Welcome. Today I will tell you a bit more how music alters brain development, which is a longitudinal twin study on sensorimotor synchronization and brain plasticity. My name is Lina van Drunen and I'm a PhD candidate working at the Leiden and Erasmus University in the Netherlands. I will present the result that I have been working on together with my co-authors displayed on the left. The human brain goes through a period of dynamic structural changes, and prior work already revealed that cortical and subcortical regions show rapid gray matter decreases between childhood and early adulthood. This process is also called maturation, where the brain starts efficiently specializing. Yet it is currently unknown whether these developmental patterns, reflected in steep and less steep declines, are indicative of sensitive windows, where experiences would have heightened effects on brain developmental patterns. Possibly, musical performance can be an environmental factor influencing brain developmental patterns, specifically during a sensitive developmental period. So only a few become musical experts, so there are many individual differences in musical performance. One example of musical experts are the Beatles.
Come together right now over me.
Well, they became experts through intensive training in combination with certain genetic predispositions, such as 50% of the variance of rhythmic ability can be influenced by genetic factors. Additionally, age of onset of musical training in childhood can also be an important source of individual variability, where early training can contribute to brain development. Therefore, studying how musical performance relates to brain development offers us a unique opportunity to investigate the genetic and environmental factors related to this brain plasticity. A fundamental component of musical performance is sensorimotor synchronization. Sensorimotor synchronization is defined as the ability to synchronize motor responses with predictable events. Finger tapping paradigms, where sensorimotor synchronization is included, are often used to study musical performance. When playing an instrument, one specifically needs to synchronize their movements to auditory rhythms of an underlying beat. And this skill depends on several brain networks, including the regions in the motor and the affective network, such as the frontal lobe, which is involved in motor preparation and execution, but also the basal ganglia and the limbic system that is mostly involved in memory formation and retrieval, but also in emotional processes. The cerebellum, which is involved in movement coordination and fine motor learning, and finally the temporal lobe, which is also involved in auditory processing, beat prediction, and beat perception. So musical training, specifically during a window of enhanced developmental plasticity, may be an important contributor to individual differences in structural brain development. Therefore, we first assessed whether individual differences in structural brain development trajectories in the motor and affective network are predictive of sensorimotor synchronization performance in 7 to 14 years old. And second, we tested whether the shared heritability estimates between brain developmental slope and sensorimotor synchronization performance are driven by genetic or environmental factors. So we hypothesized that higher sensorimotor synchronization performance is associated with attenuated brain maturation, reflected in more gradual slopes of cortical thickness change than children with lower sensorimotor synchronization performance. So we hypothesized that a positive environmental factor, such as musical training, support brain development in this way. Our twin sample included 3 waves of brain structure data, starting with 489 participants between 7 and 9 years old. At wave 3, we collected sensorimotor synchronization data and questionnaire data involving musical experiences across their lifetime. So for example, 36% plays or have played an instrument, 23% practice between 1 and 5 years, and 4% practice already more than 5 years. 6% of the samples started playing before the age of 7, 26% after the age of 7, and 68% have not started playing yet. So children were instructed to tap on a percussion pad with their dominant index finger. The first part was out phase, where children were asked to tap alternately with the tempo that was produced by the metronome. The second part was music cues in phase tapping, in which participants were asked to tap along with 4 different songs. This is one example of a song.
Bruises on both my knees for you, don't say thank you, hold please.
We operationalized sensorimotor synchronization performance by computing how stable children tapped related to the beat. Latent growth model results revealed that cortical thickness decreased between 7 and 14 years of age. This is in line with prior studies. Furthermore, volume in subcortical regions increased in this age period. And we want to emphasize with these figures that the individual trajectories differ if you look closely to all the individual lines in these figures. So more so for cortical than subcortical brain regions. And we were interested in whether these individual trajectories were predictive of sensorimotor synchronization performance. Well, in total, 5 brain regions were associated with sensorimotor synchronization performance. And here I present 2 examples of our regions of interest. In line with our hypotheses displayed on the left, we observed that indeed a less steep decline of cortical thickness in 2 frontal brain regions were associated with better sensorimotor synchronization performance. The x-axis represents the slopes and the y-axis represents sensorimotor synchronization performance, with one defined as perfect stable tapping. As you can see, a less negative slope was related to higher sensorimotor synchronization performance. For our second aim, results revealed that in the pars triangularis, 33% of the covariance in heritability estimates between brain developmental slopes on the left and sensorimotor synchronization performance on the right was best explained by shared environmental factors, depicted in yellow. We found similar results for the pars orbitalis. So I hope that you will take away from this talk that sensorimotor synchronization performance was related to structural brain developmental trajectories of the motor network and affective network, including regions as the fusiform gyrus, the pars orbitalis, the pars triangularis, the cerebellum, and the amygdala. We observed that mainly attenuated brain development was correlated with higher sensorimotor synchronization performance. And suggestively, there is a sensitive window of brain development where musical training affects brain developmental trajectories to a larger extent. A substantial part of the relation between brain developmental slope and sensorimotor synchronization performance was driven by shared environmental and unique environmental factors. And possibly musical practice, environmental influence, has a larger influence than musical talent, which is a genetic factor, on individual differences on brain development. Thank you so much for listening. If you have any questions, you can find me on Twitter or you can ask me questions on my email. Thank you.